not a line, but a polyline. And this polyline should go from left to right. So it can go like this and diagonally like this, but it can't return to the left. It was said that every vertical line should intersect this border at exactly one point. And that essentially means that this line should go from left to right. For example, like this. And then all points are split into three parts. One is above the line, one below the line, and one on the line. And you need to create such a split where the difference between the maximal and minimal part is minimized. So it was the problem. How does one solve? As surprising as it gets, you should use dynamic programming. More specifically, what is the state in this problem? How do we? Let's build our line from left to right. So suppose we have already built our line up to some point, for example, up to here. Then for all points that are to the left of the current x, we can know whether they're below the line or above the line or on the line. So let's do the following dynamic programming. Again, maybe we can. Let's sort the points by the x coordinates first. And when x coordinate is equal, by increasing y coordinate. The second part is not important. The important part is you sort by x coordinate. So I think you could just disregard the coordinate sizes when x coordinates are equal. So points are sorted by x coordinate. Then our dynamic programming will be first index is I. The point up to which we build the line. So it's last point of a line. Last point of a line. Of border line. Of border. Then N1 is how many points are above the line of those with numbers less than I. How many points with numbers less than I are above border. And N2 means below, the same but below border. And we'll calculate this array in the order of increasing I. And the value in this array will be either true or false. Is it possible or not? You have such a split that ends at point I, has N1 points above the border and N2 points below the border. You see, how does one invent such dynamic programming structures? So the idea was, suppose we construct a part of our border, that the only thing that is really concerning to us is how many points are above, below, and on the line. It is not important which ones are where. So we can only remember the numbers in our dynamic programming, not the actual points that are above or below. And we don't give a certain number because their sum is equal to I minus 1 or I. So the number of points of certain kind can be calculated from these numbers. So we don't need it. Yeah. Okay, so how do we calculate this? Not so difficult ways. So again, consider, suppose I is the last point of a border. Consider the previous point. Then we have this. Can I N1, N2 is, how to write it, or over or G less than I such that Xj is less than Xe. So over all points to that. Then N and this is important, some kids have missed it, and no point lies exactly between, lies on the segment. And so this is in worst case again 100 iterations. And to calculate the number of points you need another 100. So it is like 100 to the fifth power, which is slightly too much. So we need to speed this up somehow. Well, there are some observations that how to speed this up. One is that not all N1N combinations of N1 and N2 are possible. For example, the sum of N1 and N2 should be less than I. That leaves you with much fewer possible variants. But how do you account for that? To properly account for that, you should. So this idea when you in dynamic programming, when you calculate some number using previous numbers, is called backward dynamic programming. But there is also forward dynamic programming. You can do it the other way. So when you have calculated this number, you can consider what will be the next point on the polyline and add the new values there. So that way you will do this only for those N1 and N2 which are possible. So your program might look like, so calculate, after calculating G, N1, N2, you could do for E. When E, where E is the next point, can E N1 plus something, N2 plus something equals true.
Jesus.
So if this is true, then we can consider the next point and put true to all borders at the end of this point and have N1 plus how many points are above the segment and 2 plus how many points are below the segment. This will speed up the program. I think it will speed up it sufficiently so that you can pass. But you could speed up this program further by using the following idea that so suppose we have this forward dynamic programming and you are considering points that are next after point G. Then if you sort all other points by angle, so sort all other points in the order of angle. And remember, all of them are to the right because we sorted our points in the order of increase. And then how to say? And then when you go from bottom to top by angle, then to calculate the number of points above and below the segment, you can use an interval tree to avoid doing 100 iterations to check all points. But you could, you see, the points that are below the segment are those which have a smaller angle. So you should check the number of points that you have already seen, and that have x coordinate less than the current x coordinate, and that's what interval tree can do for you. So you basically create interval tree by x coordinate and put ones when you encounter points, and then when for each new point you see how many ones are in the beginning of this interval tree, and that means how many points are below the segment. But I think this was not necessary because I think it passed even with this optimization because many of those hundreds are actually much slower. So if we restrict N1 and N2 so that their sum is not more than I think that reduces the number of possible cases 6 times. Here we only consider points that are between G and E. And that on average reduces the number of cases, I think, also 6 times. And then here we consider only points G that are more than E, so we reduce the number of cases on average 2 times. And together with all this, I think this makes it work in time. But if it doesn't, you could use this speed up. Yeah, and the end, of course, this dynamic programming is nice, but you have to handle separately this segment and this segment. So one of them is used to set the initial values for this dynamic programming. So for each point, you should count how many points are there below this half-life and above this half-life, and set appropriate value to true. And then in the end, to get the answer, you should for each calculated, for each true value in this array, calculate how many points are above and below the half-life, and again, then when you know the numbers, you know the number of points above, below, and on the border, and you can get the best split that has the minimal difference between maximum and minimum. If you get all splits, you can find the best among them easily. See? Okay, so that was this problem. Okay. Problem B about financial software.
Chutes. Você tem dúvida? Petr.
Yeah.
He has a question.
Yeah.
Fala alto, Chutes.
Yeah. Yeah, that's a good point. Because number of points above and below doesn't depend on one end. So you can calculate it only once for each priority, and that would also be fast. Yes? That's a good point. So this internal tracing is necessary. Yeah. Okay, so problem B. About financial software. You had a sequence of numbers and had to find the longest subsequence of the sequence such that each two adjacent numbers differ but by at least k. So if k equals, I don't know, 3, then no, better 2. Then the longest subsequence where each two other numbers differ by at least 2 would be 1, 5, 2, 8, yes. And even with 3, it will still be 1, 5, 2, 8. And with 4, it will be 1, 5, maybe, or 1, 8. The length, maximum length, will be just 2. How to solve this problem? It's kind of becoming a recurring theme in our course, but it is solved by dynamic programming with an interval 3 inside it. So we had 100,000 numbers, so we should create an envelope solution because n squared, which is a zero-base dynamic programming, would be too slow. But what is zero-base dynamic programming? So if you calculate length of E, the maximal sequence that ends in number E, then the formula will be simply length of E is 1 plus maximum over all G less than E such that AE and AG differ by at least K, length of G. So, this is a very simple formula, and where does interval 3 come from? We can split this equation into two possible cases, which is equal 1 plus maximum of two values. First is maximum over AG is more than equal than AE plus K, length of G, and maximum G less than E, AG less than equal AE minus K, so length of G. So either the previous number is smaller or larger, And in each of those cases, we can see that we get a query on a segment. So on a part of values that is more than or less than some value, and that's what an interval tree can do for us. So how would our solution work? We would have an interval tree where we will put, after rotation a number at position AE, we will put the number length of E. And then to find these maximums, we will do a query for a maximum on a range on this tree. This is almost the correct solution, but it has one problem. That the numbers are too big, I think. Yes, they are up to 1 billion. And we can't have an array of size billion. So we again need to compress the numbers. What does it mean? We need to replace each number A by its number in this sorted order of all A's. So for example, we will replace this sequence with 1, 4, 2, 3, 5. So again, we replace each number by its position in the sorted sequence. This does not work like that easily because this plus k thing is not the same when you have reduced the numbers. So you have to recalculate what should be instead of this plus k. And this is easy to do. So suppose you have sorted all A's and you have a sort, I don't know, let's say B are sorted A's. Then for each number, you should find the closest number to the right that differs by at least k, and the closest number to the left that differs by at least k. If k was small, you could do that by just going from each number until you find a bigger and a smaller number. But k can also be big, as far as I remember. Yes. So, but here we can use the standard idea that we can move 2 pointers in our array. So what do I mean? So suppose that we found the closest number to A1 that is greater than A1 but by at least k. Suppose it is B1 because B is sorted. Suppose it is B5. Then in order to find the closest number to the right of B2 that is more than B2, we can continue from B5 because we should not check the numbers from here to B5 because they will, if they were less than k close to B1, they will be less than k close to B2 because B2 is bigger. So we kind of move 2 pointers. One points to our current number and another points to the first number that is bigger than by at least k. And when we go to the next number, we continue moving this pointer to the right. And because of that, the whole running time of this is linear. Because each of the pointers does 1 plus of the whole array. So in linear time, for each number you have found the closest number to the right that is more than by at least k. And the same you can do by finding numbers that are less by at least k. This is an important idea, and I want to totally repeat this idea. But of course, in this problem, you could just use a set and do some lower bound queries into it, because you could afford n log n for this part, because other types of solutions still works on n log n. But I think it's important to know that sometimes you can do such optimizations from n squared to n using this moving pointer idea, and it arises in other problems as well. So please keep it somewhere in your mind. That sometimes it's not the best. One of the best examples of that is say if you can formulate the problem. Never mind. So that's all about this problem. Questions? in this problem, you're given a graph, and you're given a path in this graph, and you need to change the weights of edges of this graph by the smallest possible value, so that the maximum change is the smallest possible, such that the given path becomes the shortest path. So you have some graph. And there is some path in it that is given to you from vertex A to vertex B. And you should change the weights of edges that are given to you, some initial weights. Such that this path becomes the shortest path from A to B. How does one solve such problems? Here we can consider ourselves a smaller problem. Instead of trying to find the smallest possible change, we can solve the following problem. If we knew, so if we are allowed to change each weight by at most 5, can we make this path the shortest? If we are, so if we have some upper bound on change of weight on each edge, then we are allowed to change the weight of each edge by at most m. How to make this path the shortest? Is it possible to make this path the shortest? It is quite obvious. It is quite obvious that the best way to do that is to reduce all edges along this path by m by maximum amount. But they can't become smaller than 1, so you should reduce it by m, but not smaller than 1. For example, if m was 5, then this would become 1, this would become 95, and this would become 5. So we reduce by 5, but not less than 1. And for all other edges, you should increase them by at most m, so that other paths become worse. Basically, it is the only thing that makes sense. So you should put 7, 8, 15, 8, 6. You see? And then check if this became a shortest path. I want to try to prove this formally, but I hope that this is obvious to you as well. So this is the best way to make this path shortest. To make the edges on this path as short as possible and all others below this possible. So that's the way you check if you can make the path shortest if you change by at most m. And then to solve the problem you employ binary search. So the minimal possible change is 0, the maximum possible change is, say, all times per up to 10,000, so the maximum possible change is 10,001. So and then you do binary search. So you do it like this, like which writes a good point how to write proper binary search, which I want to talk a bit. So I think that to write a good binary search, you should always have some, how to say, have some invariants. What do I mean? You should, the variables left and right that you have in binary search usually should have a meaning. So here we would say that if we use change by at most a, change by at most a, the path is not the shortest. If we change by at most r, the path is the shortest. So when we have these two assertions, it's easy to write the binary search, and so how would binary search go? While some condition m equals left plus right divided by 2 if enough of m right equals m, otherwise left equals m. So where enough of m is the method that checks if it's enough to change by mode of m to get this positive shortest. So there are two questions here. So why am I, well, I'm talking about this invariance. In this case, where the variable is floating point, it is not very important. But if this were, so if for example we were allowed to change only by an integer amount, then it is important to have this invariant so that you know, for example, should you write this or like this, or like this. Because in binary search, sometimes, if you, for example, write the standard binary search to find an element in an array, usually one of these equations has -1 or +1, and so on, in order to avoid that. So, how would I solve this problem if the numbers were integers? They are only allowed to change for integer. I would say that L equals -1. Why? Because I want to be sure that if we change by at most L, the path is not the shortest. And for 0, I'm not sure. Maybe the path is already the shortest. So L equals 0 would be a problem. Then the condition would be, so we know that for L it is not good and for R is good. Then the condition would be that there is at least one number between R and L. So I would write R minus L more than 1. Again, and that would be all the code for integers. And there would be no +1s or -1s because my invariants are such that by checking if the value is okay, I should either put it in one class or in the other class. Again, I hope you get the point. So the point is when you do a binary search over integer domain, you should try to have an invariant. What does L mean and what does R mean? And that way you can not make a 0/1 mistake in your code. See? Okay, so in this problem this is irrelevant. Because everything is floating point, and this is not important, and the only thing that's important is what to put here. There are two philosophies for that. One philosophy is that you put something like this. R minus L is less than 1, like this. It is usually a normal approach, but sometimes, how to say, sometimes it leads to problems if, for example, this value of R was so large, the possible answer so large. For example, if it would be 10 to the power of 12, then together with this, that would make the relative precision that we require, so the delta of R and L compared to the value 10 to the power of 21, which is more than precision of a double value. And so this might never happen. So in order to avoid that, it's usually better to have relative precision here. For example, like this. Here we know that R is more than L and thus more than 0, so we can divide by it safely. And we can use relative precision to find the value. This can also have problems if the correct answer can be too small. So the best possible way would be to have both of those conditions. And R minus L less than 1e minus 9. That way, if R is very small, like 0.00001, this condition can never be satisfied, and this will be satisfied indeed. And yet another possible approach is replacing all this by a form. For E equals 1, E equals 100, velocity, just do 100 iterations. And that will hopefully get enough material. This approach is good, because in most problems, time limit is anyway the same for all these cases. So time limit allows you to perform a certain amount of operations, and it doesn't make sense to perform less because you will have more precision, and it doesn't make sense to perform more because you will not fit in the time limit. So there is always some amount of iterations that you can get to safely stay within the time limit, and you should just do it. It doesn't work if your program involves more than one binary search. Then it makes sense to make them as fast as possible. But in this problem we have just one, so we can just have a fixed number of steps. And to determine the number of steps, you should run and see how long your program works. And this contest, it was not possible because the server is another as your computer. But in almost all official contests, usually you either have a way to find out what is the difference, like they publish the specifications on the server, or it is just on the finals, for example, it's just the same as your computer, so you can know how long it runs and make guesses on what is the correct number. But on the finals, it's not most time. Okay, so that's all about this problem. Yeah, the final touch. To find the shortest path, I think you could use just the usual Dijkstra algorithm, which runs in n squared, because you find only 1,000 services. But this problem could be made, so you would be required to use the Dijkstra algorithm to find the shortest path in m log n time. I hope you know it. If you don't, please read about it or ask your friends. I'm sure that some of the people in this room know how to find shortest path in m times log n times. Or m log n. To find the shortest path from one vertex to any who is non-negative weights. So-called Dijkstra with heaps. For example, it is described in Introduction to Algorithms in main articles. So I won't be telling about it because it was not necessary in this program, but still, I think it's good to know about it. Sometimes it's useful. Not frequently, but sometimes it's useful. Okay, problem D about the night watch. In problem D, so problem D was a good example of a problem that I think such problems turn out that the finals pretty frequently. In this problem you have to do a lot of things, but the resulting solution is very, I don't know, there is nothing clever in it. The core is just again the Dijkstra algorithm in some graphs that you have spent many time to construct. So, what is the problem about? You have some polygon like this. For example, like this. And you should find the shortest path in this polygon from anywhere to anywhere, but such that for every point of the polygon, it is visible from at least one point in this path. So for example, here if we go like this, then every point will be visible from some point of this path. This point is visible from here, so the guard that works in the visual can see all the rules at some point of this path. So, how are we going to solve this problem? First, let's consider how far to the bottom the guard needs to go. I claim that if we take the first edge that goes inside, so here I say that this edge goes outside and this edge goes inside. So the first edge that how to say that the first edge of the right border that goes to the left, or the first edge from the left border that goes to the right. here we are using the fact that the given polygon is not any polygon of this form, but it is how it was set, monotone, which means that for every horizontal line, it will intersect the polygon on a segment, not two segments. So pictures like this are not possible. They're forbidden. Because this line will intersect in two segments. So our polygon, monotone polygon, can be described really by two sides. Its left side, which goes like this from top to bottom, and right side that goes the same way. So we find the first position either at the right side that goes to the left, or at the left side that goes to the right. Here, the first of those two will be this one. So I claim that the guard should never go below this line. So if we draw this line, it doesn't make sense for the guard to go below this line. Why? Because consider the whole, consider the bottommost edge. To see this point, the guard must be at some point in this region. So to the right of this point. And to see this point, the guard must be at some point of this region. So to see the bottom side entirely, the guard must be at some point which is between this coordinate and this coordinate, right? And then it's not so easy to see that being in some point along this segment is always sufficient. So if you are in some point along this segment, you can see everything that is below this horizontal line. So you can see all this part from any point in this segment. And you have to be at some point of this in order to see the bottommost edge. So that's the first fact, that we don't have to go below this line, because we might as well stay on this line and get a shorter path. So if our path goes somewhere like this, then we could instead go to the same point but not below this edge. The path will become shorter and we will still see everything below. So it doesn't make sense to go below this line. The same is true for the top. So if you find the first small edge at the top, here it will be this one. It doesn't make sense to go above this one. Also, we have just proved that we should sometimes visit a point. Yes, but at the same time, we must go to this line, so we can't go further. Why? Because this was chosen in such a way that we can only see this point from this line or below. Because of this, we must at least once go below this line. So essentially, that all that I said means that we should at some point visit one point of this segment, and we should at some point visit one point of this segment. And then I claim the following, that any path from this segment to this segment, any path, will be a solution. So any path from this segment that is defined by, again, finding the smallest y coordinate so that there is an edge on the right side that goes to the left or vice versa, and on this y coordinate choosing a segment that corresponds to the bottommost edge of this part, and doing the same for the top. This defines two segments, and I claim that in this problem we are essentially required to find a path from this segment to this segment. Any such path will be so that we can see any point in the museum. Why? Because for every point in these bottom parts and in these top parts, we have just proved that we can see them from any point of the segment. And for any point in between, we can just see them because at any point we can see to the left and to the right. And that way we cover all the polygon because it's monotone. You see? So this was the trick. After we got this trick, we have this problem of finding the shortest path from one segment to other segment? Well, in order to find the shortest path, we need somehow restricted, because number of possible paths is infinite. So we need to. The problem picture contains the hint. So basically, it doesn't make sense for this path to build in any other place than the vertex. I mean, if this path has a corner, then why not go like this and it will be shorter? So the only way for this path to have a corner is at the vertex of the polygon, for example, like this. Then, okay, when should this path start inside this segment or inside this segment? So consider the last part of this path. So this is the segment that it should start at, and it goes, I don't know, like this. Then why not make it go like this instead? And that will be shorter. And again, that will be shorter. So the only way that the path cannot be made shorter is two cases. Either it starts from the end, like this, or it is vertical initially. If the path is vertical, then we can't make it shorter by moving this point. So, what does it mean? It means that if we take this segment, and on it we take all points from where we can go up until another vertex. So we take all x's of all vertices. Here there are none, but it could be possible that, well, how to say, for example, it was like this. And then we will take this x. So we take all x's of all points of our polygon on this segment. And the same for this segment. These are the starting points of the path, and these are the ending points of the path. And then we construct a graph, which can consist of those vertices that we just marked, plus the vertices of the polygon. And we should find the shortest path from any of these points to any of these points. So the graph consists of these vertices. And there is a nature of this graph if such a line doesn't intersect anything. So we build such a graph which connects any pairs of vertices that don't intersect anything. And then we find the shortest path from any of these vertices to any of those vertices by using the Dijkstra's method. And that is the answer to the problem. So we have to make a lot of steps. First, we need to consider that we don't need to go below this line, that we must go to this line, and we must go to this segment. And then we find that on this segment we can only start at the ends or vertically, and then we have reduced finally our problem to a finite number of points, and then we can construct a graph and find the shortest path. And to construct a graph, we need a routine to check that a segment intersects the polygon. That's the geometrical part of this problem. But it's not so difficult because, again, the polygon is monotone. So, it's really, I mean, it's not. You can either write a complete intersection procedure or use the property of the polygon to see that the left, if you split the border into two parts, you need to see that the left part doesn't go to the right of this segment and the right part doesn't go to the left of this segment, which is not so difficult to check. Okay? There are some funny cases. For example, if this was like this edge was like this, then our segment would be here, and we would be required to go like this. So you should not disregard in your graph edges that go along with the polygon. These edges should be allowed in your graph, otherwise you wouldn't be able to get out of this situation. Or you will get out in a bad way, in a blown way. You should not disregard the edges that go along the sides. Okay, that's basically questions. Okay.
You need to check the lowest edge from the top.
So we find in the right part of the border, we find the first edge that goes to the left. So that reduces the size of the polygon. And in the left part, we find the first edge that goes to the right, here is this edge. And from those, the one that is below. And from the top, yes, you take the first edge to the left that goes to the right. And from this group, you take the first. Because otherwise, if you don't go to this level, you don't see this point, this corner. And if you go above, it doesn't make sense because you can see everything here.
Isn't there a case in which bottom right segment lies the upper side of the higher?
Yeah, that's a good point. It can, for example, be like this. For example, be like this. In this case, basically, yeah, it's a special case you need to care about. So yeah, so it's possible that this bottom segment that you start with and the top segment that you end with are reversed. So here you should start from this segment and end at this segment, which is ridiculous. And in this case, when you detect this situation happen, it's easy to see that what you need is basically on every level between these two segments. So if you take any middle level between these two segments, then in this and how to say, and project the bottommost side to this level and the topmost side to this level, then you need to basically visit both of those areas. So in this case, you can just stand at the point, but if it was like this, then you should have come from this point to this point. So in this special case, you take a line between those two levels, project the topmost side and the bottommost side on it. If they intersect, you take any point of the intersection. If they don't, then you go from one corner of this to another. Yeah, this is a special case that is different from the main script. That's a good point. So, why is it different? Because in our solution, we said that it doesn't make sense to go below this line, that we can stay on this line. But if we don't go below this line, but rather are below this line, then it makes sense. So here we start and end below this line, and start and end above this line. So our argument that we don't go below this line doesn't hold. That's why this special case arises. Okay, now let's see. Okay, problem E. About convex paradominals. So I'll redraw the picture from the problem statement. So this is an example of a convex paradominal. So the definition is a convex polynomial is such a convex polynomial. So polynomial is essentially what we defined in the previous problem, a polygon with all sides parallel to axis. And all sides have integer lengths, and convex means every horizontal or vertical line intersected by a continuous segment. And paradominal means that on every x and y there is exactly one segment, exactly one side. So on every x and y there is exactly one side of our polygon. this side, this, and so on. So this is the definition. And we need to count the number of convex permutominos with 2n sides. The number of sides is always given, so it's 2n. N was quite small in the input, so the number was up to 30. So essentially what we need to do is to create any solution that is better than counting them all one by one. So we can try to afford some complicated DP. So for example, consider that we build our permutomino from top to bottom. And we have built it up to, for example, this place. So in order to build a DP solution, we need to think what is important to the bottom. So if we remember the whole permutominos we built to the top, then this will be not a DP, but rather an enumeration of all permutominos. In order to have a DP, we need to group some of those situations. So we need to say that, for example, this situation and, I don't know, this situation are the same in terms of what happens to the bottom. Why? Because basically the same axes are already occupied and some are free. And the two edges that go to the bottom are at the same position. Then it is essentially the same situation for the rest of the construction. And if you think more about it, then the only thing that matters is, so again, so these coordinates are from 0 to n minus 1. So here n is something out. Here n equals 7. So what matters is when we have constructed some top part of a permutomino, what matters is how many free axes are left before the left border, between the left and right border, and between the right border and right. So after the right border. So actually what matters is three numbers. N1, how many axes are free before left border, and 2, how many between borders, and 3, how many axes the same after right border. I understand this is not obvious, but this is what you have to do to solve this problem. You have to realize that even if those axes are shifted, for example, if it is like this, the number of possible completions of this permutomino, the number of possible ways to build permutomino from the bottom of the slide will be the same, because there is only one free x between those lines. So at some point we should use it. So in this case, this permutomino changes to this one, but the number of choices still the same, stays the same. You see, so how to explain it? Okay, I'll try to explain it by writing the dynamic programming program. Maybe it will explain why all these numbers are important. So, suppose that you will use a forward dynamic programming. So suppose we have calculated. Okay, so a dynamic programming would be now. So the left border is at L, the right border is at L. At the left border, this is the right border. N1 are free, as I said, N2 and 3. And we have already constructed H rows of the permutomino. So this will be our DP. one can notice that one of those numbers is not necessary because basically the total number of free rows is equal to n minus how many vertical segments we have already placed. And the number of vertical segments that we have already placed is exactly h. So for example, here we have already placed 1, 2, 3, 4 vertical segments. And we have built our order domino up to 4th level. So, or if we define h of the number of levels that we have already completed, then the total number of free segments will be h plus 1. But still, one of those numbers is not necessary because it is determined by the others. But we can keep it, it doesn't really matter. So, suppose we have counted this number. How to continue building a pairing domino? So, if we have this beginning, then in order to continue building pairing domino, we should either from this point go to the left or to the right to some okay, so at this right coordinate there will be exactly one edge. This edge will start either at this point or at this point. So what we can have to the next level, if we erase, we don't know what will happen next. So we'll have only this picture. What we can do? We can do like this. Either this one, this is one choice. The other choice is this one. The next choice is this one. The next choice is this one. And that's all the choices we have. Because there are no other free x's. So we have those choices. Because of this, we can try to write a formula. So suppose we have counted this, then we iterate over the next h. So for example, if the next h starts from the right corner, then we should try n2 plus n3 variants. So there are n2 variants for this h to go to the left, and there are n3 variants for this h to go to the right. So we would do something like for e equals 1 e is less than equal to n3 plus e, where e means how many steps do we take to the right. In this case, the new state will be we are at position what have I told you? Am I crazy? Of course, L and R will belong here. Because basically again, all we need to know is n1, n2, and n3. And where we are, again, doesn't matter. So this is equal to num. The number to the left stays the same. The number between becomes n2 plus I minus 1, and the number of free positions to the right becomes n3 minus I. So if we, in this case, if we take the rightmost position, then to the right there are no more free x's, but to the left there is one more free x. So if I equals 2, we get n2 plus 1 in the middle. And h plus 1 plus equals num n1, n2, n3, h. So here is one part called e. Now we should try to go from the right corner to the left. Then we have again for e equals 1, e less than equals n2 plus e, and go now n1, n2 minus e, n3 plus I minus 1 plus equals the same. So that's, and two similar loops for the left edge. So we can try to go from the left corner. So this is roughly the DP for this problem. There is one more detail that we have overlooked in this solution. Is that our pairing domino must be convex. We don't enforce this. We enforce that it is convex in the horizontal sense. Because in each horizontal line we have a range from somewhere to somewhere. But currently it can become like this. And this is not convex. So we have to forbid this situation. In order to forbid this situation, we should only allow for the left edge to move to the left before it has moved to the right. So after the left edge at least once has started moving to the right, it should never come back to the left, so that we don't have this situation. And the same for the right edge. After it started moving to the left, it should never come back to the right. So we should, to our ODP, we should introduce two new parameters that are booleans. So can C1 is C2, which means can left edge go right and go left. And this means can right edge go right. So here, what would we change here? This loop, when the right edge goes right, we should only do it if C2. So this loop should be done only if C2 is true. And when we go to the left, so here, if C2 is true, then we do now C1, C2 equals, and again, here the same change is required, C1, C2. But here, when we go to the left, we should forbid to go to the right. So here we will write now C1 false. So we are forbidden to go to the right edge, to go to the right, if it has gone to the left. And here we have the same. So here we have now C1, C2, and 1, and 2, and 3 edge. That way we are enforcing our polynomial to be convex with respect to vertical lines. We have two new Boolean parameters that say that our left edge can now go only to the right, or the right edge can go only to the left. And yeah, this is basically, and the only thing that remains is to say what are the initial values and what is the answer. The initial values is the possible positions for the top edge. So basically, none, true, any two numbers, a, I, j, and k, such that their sum is equal to n minus 2 and 0. So these are the initial values for 1, or whatever we number h from. And the final values are the same for the bottom. So the final values are none, anything, e, g, k, any, e, g, k, and m. So these are the final values. And we should sum them all to get the total number of polynomials. And also this problem required big integers. The number would be very big. So again, we should either write it in Java or in C++, but we have to implement big integer iterations. But luckily, in this problem, the only iteration you need is addition. So addition of two big integers is not a very complicated code. Just do it from right to left. And don't remember about carrying. Okay, this was one of the most difficult problems of this contest, but it is like 5-dimensional dynamic programming. But since those numbers are small, so this has only 2 variables, this has only 2 variables, this has 30 variables, this has 30 variables, this has 30 variables, and this can be calculated from this thing. So the total number of variables is roughly less than 1 million. And in reality, even a bit less. Because not all combinations are possible. Okay, so
I think that would be something like that. If you have, if you can go to the right, Okay, that's fourth. Then you go until you can. So because if you go to the left, you won't be able to come back to get the ones to the right. So you can go to the right while you can, and just go to the left if there is zero to the right. So you can eliminate those two rules. Right?
Excuse me, what was your conclusion?
I could eliminate those two rules that you got.
No, but how do you tell if you were to the rightmost? And so if you go in here and then went several steps here, you should remember that you already were here. You should somehow.
If the moment that I start going to the left, I will always go to the left.
Yes, but when you go further, you should remember that you're going to the left, not to the right.
Okay, but if I can't go to the right yet, if n3 is more than 0, I have to go to the right, because if I go to the left, I won't be able to
mean that you can store the checks at n3. When going to the left, you should always go to the closest possible because you have no chance to come back.
Yeah, and the right I can go everywhere. So
yeah. I think that's a good point. You should do it like that to reduce the number of states. But that's, even this number is not, but yeah, you're right. So basically by eliminating the states that are impossible to complete, you can further reduce the total number of states. There is another solution for this problem that involves the idea that every permutomino can be split like this. So if there is some permutomino, we can find, for example, the leftmost vertex at the top, the bottommost vertex at the left, the rightmost vertex at the bottom, and the topmost vertex on the right. And between those 4 points, these things are like stairs. So they only go in 2 directions. Here to the top and to the right, here to the right and to the bottom, and so on. So you could calculate the number of those things multiplied by the number of combinations to choose part of this that goes here and goes here, and then subtract some self-intersecting. So you could, I don't know the solution, but there is a solution that involves basically calculating the number of such stairs and then multiply it by certain binomial coefficients to get the total number of possible permutominos. But it is much more complicated than this, so I don't suggest you write it. But if you are interested, you can try to figure it out. I don't think it's impossible to figure it, just has some issues. Okay, so that was problem E. Problem F, about substring search. Problem asks, you had a string like A, B, E, A, and you had another string like C, C, A, C, D, and you are asked if there exists a substring of this second string, for example this one, that can be obtained from this string by change of letters. So by applying permutation letters, changing equal letters to equal ones and different letters to different ones. There are 2 possible approaches to this problem, as to almost any such substring matching problem. So first I will describe the the proper approach. The proper approach is to use the following idea. Suppose we take this string and replace each number by the distance to the closest, each character by the distance to the closest such character to the left. So, for example, okay, this is a bad example. Let's, for example, start with this example. It's simpler. So here we will have, there is no such character to the left, so we have infinity, 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 1, 3, infinity. So we have distance from this C to this C is 3, so we have 3. And for this string it is infinity, infinity, 1, 3. Why are we doing this? Because by replacing the character by distance to the left of the same character, we are kind of how to say, ignoring the permutation. So now, as you can see, the start string and what we have to look at in became the same. So now we can perform just the usual substring search for this and this. For example, using Knut-Morris spread algorithm. But this has a catch. So if the string originally was like I said, then this number would not be infinity but 1. And this would not be just substring search. So the problem is that some characters in the string can also appear before, and that ruins our idea. But there is a way to overcome that. So let's understand what do we need to do. We need to find a match for this sequence and this sequence such that each number matches exactly, and when there is an infinity here it should be either an infinity or a number that points outside the string. So if we have infinity in position E, then here so it should be either an infinity or a number that is more than equal to E. So here it should be at least 1, here it should be at least 2. So for example, if we had like this, it would be like this. So if it was 8, then it would be infinity and 2. So here we should allow any number that is at least 2 or infinity. So we have this Knut-Morris spread with we have this doing something matching with some additional restrictions. And it turns out we can transform the Knut-Morris spread algorithm to matching substrings to allow these restrictions. So what is the Knut-Morris spread algorithm?
Petr, before you go on, one question. How would you compute that array fast enough? Because
you go from left to right. And remember the last position for each character. There is only 100 of those.
Okay.
And basically just
cool.
store it. Yeah, that's a good point. So, what is Knut-Morris spread algorithm? Knut-Morris spread algorithm uses the following idea. That at each moment of time, so if we are trying to find a string in a longer string, then we will go from left to right among the longer string, and at each moment of time we remember the longest start of the string that we try to find. So the longest start that is here, that ends in this position. So for each position, we find the longest start of our string that ends in this position. Why is it enough? The Knut-Morris spread algorithm claims that all other starts can be obtained from this start by using so-called prefix function or fallback function. What does it do? Prefix function is prefix function for a string. So if there is a string, I don't know, ABC, is the longest prefix of the string that is also a suffix of the string. So here it will be ABC. And for example, if it's ABA, then it will be ABA because it's the longest prefix that is also a suffix. And so what Knut-Morris algorithm uses and what is the main idea why it works is that we have this match here. All other shorter matches of prefixes of the string to this string can be obtained by taking the longest suffix of this string that is also a prefix of the string. Because what can we see here? Suppose there is a shorter match, then it is equal to somewhere here. But it is at the same time equal to somewhere here. So it is exactly what prefix function defines. So again, what is Knut-Morris spread algorithm based upon? It is based upon the fact that all, in order to enumerate all matches of prefixes of strings that we need to find that end in a given position in the strings that we are looking inside, we need to take the longest one, then take the prefix function of the longest one, and then take the prefix function of the prefix function of the longest one, and so on. And then, how does the algorithm of Knut-Morris-Pratt algorithm works? So it is like this. So suppose we have our prefix function stored as prefix, and we have our length means the longest length that matches now. So we will the longest string for e equals 0. E is less than s size plus e. We go like this while I'll write the code and then explain it, because it is kind of traditional way to write brackets. So if s is a long string and t is a small string, so if s equals t 10 plus 10, break. If length equals 0, break. Length equals prefix length. So this is the standard way, I think, to write Knut-Morris-Pratt algorithm. Yeah, when if length reaches length of t, then we found the match. So what does it do? When it reads a new symbol of the string, it has length towards the longest match. We check if this longest match plus this symbol is still a match, then it is the new longest match. If not, we go to a shorter match by taking length equals prefix length. We go to the next. So we find the first match, which can be enlarged by adding this symbol, and that is the new longest match of the prefix of this string to that ends at the given position. So this how the Knut-Morris-Pratt algorithm goes, and it has linear running time because we only increase length by once each time, and because of that, it might seem that this can be quadratic if this loop runs n times and this loop runs n times. But in reality, this loop cannot run too many times in total, because every time it runs, length is reduced. And it can be increased by at most once. So the total number of reductions is the same as the total number of increases, or not more than the number of increases. And that's why the total number of executions of this loop in overall time is n. And so the running time is n, this algorithm. And building the prefix function itself is performed in exactly the same way. But instead of s, you put here t. And we start not from 0 but from 1. So idea is that, again, in order to find the prefix function, so suppose you have found the prefix function for this string. So you know that this is equal to this. Then how do we find the prefix function for this string? Again, we should check if this character matches this character, then you should enlarge it by 1. Otherwise, you should take the next smallest prefix function of this and see if this character matches this character, then you enlarge it by 1. So basically, the construction of prefix function is just the same loop, but we replace here t, and here you start from 1. And then you should store the prefix function here. So you say, after this, you say prefix of e plus 1 equals then you put it here. And so this will be the construction of prefix function. Okay, is it clear? I mean, if you know that how Knut-Morris-Pratt algorithm works, probably know that, but if you don't, I hope you get the general picture, and if you don't get the details, you can ask your friends or me after this. Because this is not about that. So, what is important, again I will revert to the old version. So is that Knut-Morris product algorithm can be adjusted to work with this infinity idea. So what will we now do? Our prefix function will store our prefix function will be exactly the same. But how to say? When we are running this algorithm, variable len would have a new meaning. The new meaning would be it is the longest prefix of this string that matches at our current position with respect to this idea that every infinity should be matched to either infinity or to a number more than its position. Why? And so the only change to this algorithm would be here you change as if equals tlen or tlen equals infinity and as if is more than equal than len or len plus 1. You should figure this out. So the idea is that we do the same matching, but we allow matching of infinities to sufficiently big numbers. Why does it work correctly? Now here is the key part. It does work correctly because of the following idea. That suppose in this match we have matched here we have infinity and we have matched it to a sufficiently big number, I don't know, 4. Then if we go to a shorter match, so if we go to a match like this, which also has this infinity, and here it will correspond to a match like this, this number stays sufficiently big. So because we have reduced our match, sufficiently big is sufficiently bigger. It is only bigger. So it is still okay to match it for infinity. So when we reduce a match, every number that we have matched for infinity is still okay to match for infinity. That's why it is correct to allow this match in this algorithm, because the property that to find all matches you still have to apply prefix function stays. That is the point. Okay, I think that's basically it about the first solution to this problem. What questions do you have? So the implementation is written on the blackboard, but so I mean you should be certainly able to write a solution now, but I mean in order to be able to invent such solution, you need to understand the proof. So you need to understand why does it work with infinity, and I hope I've explained it, but if you don't understand, please ask me.
I got a question. The correct meaning, I don't know if I have it clear, is the meaning of the infinite. I'm guessing that the correct meaning is just what says in problem statement about a permutation, right? When I don't have two letters equal in the string, two letters that are the same in the string, in the same string that I'm going to match in the text, right? That's the meaning of the infinity for the case.
Yes, so meaning infinity is that yes, so this is the first time that it appears. It didn't appear before.
Okay,
so you can match it to any letter.
And then when we are computing the prefix function of Cannon-Morris-Pratt, the infinity will just be like
any character.
Oh, exactly. Okay.
Yes, so we should only mention infinity to infinity. But I mean, we could still have this. So this change, we can also add it to the computation of the prefix function, but it will never trigger because in the prefix function it will be impossible. This will be impossible. As int cannot be more than len because be infinity, just like infinity. Otherwise, it will be incorrect. I think. Or not. No, I don't. So when we use the prefix function, I should do the same. For example, consider this example. So your string is A, B, BB. Then you have like infinity, infinity, 1, 1. So what should the prefix function in this string? 0, right? Okay. Let's do it like this. A, B, A, B.
One more letter.
Yeah, no, one letter would be removed. So suppose we have this string. What should be prefix function? I claim that it should be 2. So I should say that this prefix is equal to this suffix. Because every infinity matches something that is more than equal to its position. Why is it important that it matches it like this? Because suppose that we have a string AB. Suppose we have the same AB, and then again AB. Then here we would have infinity, infinity, 2, 2, 2, 2. So after we have found this first match, in order to find the next match, we need to apply the prefix function. And here the prefix function should be 2 so that we don't miss this match. Because the same rule applies for the prefix function. If some number is more than the position of the infinity, it should match. So that we don't miss this match. So yeah, when constructing the prefix function, we should also have this clause. Or alternatively, non-Poirot operator can be viewed in the following way. So it is essentially a construction prefix function of string T, some character that is not present in any string S. So we construct the prefix function of this algorithm of this string, of this big string. Then the positions where T is in S are exactly the positions where prefix function equals the length of T. If you take the positions where prefix function is equal to the length of T, that will be the matches. So Poirot can be viewed not as two parts construction and then searching, but as one part, just constructing the prefix function. Okay. Yes, there is some confusion. I agree with this, but that's one solution. The other solution is much simpler, but it's not proper. So in the sense that you can never tell whether it will work or not. But the other solution is to use hashing. What is hashing? So the idea is that we should, instead of the string, calculate some number that will be the same for strings that are only different by permutation of letters, and so that we can do a match, and still different for strings that are not the same. So such number is called the hash, or hash function of a string. Which hash function of a string will work for us? What are the requirements? Two requirements I have already said. And the third requirement is that we should be able to compute the hash function for all substrings of the string quickly. So it should not run in time equal to the length of string. It should be able to compute it faster. I propose the following hash function. So suppose we have a string A, B, A, C, A, let's write down the positions of all A's. So for A's it would be 1, 4, 6. For B it would be or even like this 1, 0, 0, 1, 0, 1. So we put ones that were that we have a letter. For C it would be 0, 0, 0, 0, 1, 0. For all others it will be all zeros. Then we calculate the hash of this The simplest way and the good way to calculate such hash is to calculate, take a prime number, p, and then calculate this as p plus p to the power 4 plus p to the power 6. So we take p in the powers of the positions of flux. Here it will be p to the power plus p to the power 3. Here it will be p to the power 5. Here it will be 0. We get all those hashes. And now we need to combine all those hashes in such a way that does not change when we compute letters. So we need some operation that is the same after permutation. For example, addition or multiplication. So we can take and multiply all these hashes. Or take and add all these hashes. And get the one big hash of a string that will be the same if we change the letters. So if the string was B, A, A, B, C, D, then what we will have is essentially these two would switch, and these two will switch. And their product or their sum will still the same. So this hash will be the same for equal strings after permutation of letters. But it might be different for, might be the same for different strings. So taking a sum is a bad idea, because if we take a sum of all these values, as you can see, it will be the same for all strings. It will be just the sum of powers of p. It will, with all powers. P plus p squared, plus p cubed, plus p 4, plus p 5, plus p 6. It's a bad idea. Product is better, but still not very good idea. Because I think it's quite easy to construct two numbers that will have the same product. What have worked in this problem was taking the following. So you have these hashes, then you add to each of them a constant, q, and then take a product of those. This has worked. So this, where p is some prime and q is some constant. Maybe better also prime. And you take a product of all this, and that product. And this will be a hash. So the idea is that basically, why do I think that this hash is good? So why do I think different strings will have different hashes? I think that it's not probable that with different distribution of p's, the product will be the same, because essentially what I'm doing is I'm taking q plus something times q plus something times q plus something, and so on. And this, in case I have a collision, so two strings match. That means, so to place A1, A2, A3, this is equal to q plus A B1. So suppose two strings happen in the collision. Then what happens is actually, what I claim is that this collision should be rare. Why? Because if we treat q as a variable, so if q is a variable, then this can only happen when all a's and all b's are the same after permutation. Because these a's are the roots of the polynomial. And this is some polynomial over q, and these are its roots. And each polynomial has only one set of n roots. So these are the same after permutation. So the only way this can happen is that we are unlucky and our q was sorted, but for almost all q's this will not happen. That gives me the reason to believe that if I choose a random q, that all the cases prepared by juries, this will not happen. So that's why I believe this is a good hash function. The other question is that how large should these numbers be? So obviously I can't calculate these numbers exactly, because they will get very big. P to the power of 100,000 is too big. So I have to calculate them modulo something. If I take them, for example, in int, or modulo 2 to the power 32, that's not a very good idea. Because, how to say, the theory is that, also known as the birthday paradox, says to us that in order to have a collision, we need square root of n random numbers. If we take square root of n random numbers, with a good probability there will be a collision. So if our n number of possible hashes is 2 to the power 32, then we need 2 to the power 16 or 60,000 to get a collision. It's quite likely thus that out of 100,000 to have this problem we'll have a collision. So it's a validity. But if we calculate the hash in 64 type or long, then the probability of a collision will be 2 to the power of the number of items for a collision will be 4 billion, and that's too big. So in almost all cases there will be no collision. So the rule of thumb for choosing the range for hash function is use in 64, because it will almost probably not lead to a collision. But yeah, because basically the number of comparisons you can make in your program is only at most several million, so the chance of collision are small. But it is possible to create a situation where you need even bigger domain for hash, but usually in 64 is enough. So, returning to our solution, after all this philosophical talk, how to implement it? How to quickly count this value? It's easy to see that when you switch, so we have these 6 letters, Z, and we check if it matches our string. Then we need to check next letter, so we need to shift by 1 letter. It's easy to see that each of those arrays is changed in a very simple manner. We add to the end either 0 or 1 and erase the first letter. Here add 0 and erase the first letter. In terms of this, it corresponds to dividing this number by p. To erase the first letter, we need to subtract p if the first letter is equal to 1, and then in the end we need add p if the new is equal to 1. So let's write some code. How would the program implementing this solution look like? So we have age array, let's say, with 128 items that contains long nodes, which will contain the hash, the sum of those p's for each letter. Then we go along our string for in key equals 0, e less than s size plus e. So what we need to do first, we need to subtract the letter that goes away. So if e is more than t size, so we already have a letter that goes away. Then we should say h s I minus t size. We should subtract p. Then we should, for all, for in g equals 0, g plus 128 plus g, we do h g, we multiply it by p, or no, divided by p. And divided by p is a bad idea. So what we need to do to avoid dividing by p is we need to, how to say, to reverse the order. So we should say that this is 1, this is 2, this is 3, and so on. That way we'll need to multiply by p. But the downside is that we need to subtract not p, but p to the power of t size minus 1. And then we should say h as e plus equals e for 1. And And so that's how we calculate our hashes in an efficient way. So for each character, we calculate the new hashes in only 128 iterations. And then we calculate our big hash as a product for of Q plus H. And then we check if this hash matches the hash of the original string. So here is the solution of these hashes. The good side is that you don't have to think much about it. You basically calculate some hash that is the same. By the same, I mean that you have a product here. When you can use letters, but it should be different for different strings. And for that, you need to have some intuition. So it basically, it can turn out that this bit solution it doesn't work. And I mean, your hashes are not good. Some do different things. Gain the same hash and you have an answer. It's a very bad situation to be in. Because either you try to change your hash or try to tune it, or you have to invent a normal solution. But in many cases, writing a solution with hashes is a very quick way to solve a problem. For example, the standard problem where this is where much better than the proper solution is sub-square match. So suppose you're given a square of letters and a big square of letters. You need to find the image of this square inside the square. Then the proper algorithm would be doing something like KMP, Cook-Morris-Pratt algorithm, but in 2 dimensions, which is not so easy. But with hashes, it's quite easy to calculate some hash of the square and quickly calculate hashes of sub-square of the square by using the same trick with polynomials. That if you have a polynomial, then once you shift from left to right, the hash changes in a simple way, if you have a polynomial. So, this is the most famous problem that is solved by hashes much easier than by proper algorithms. But with hashes, you can never be sure that you don't have a collision. So, you can, but if you have, like I explained, this thing with polynomials, it explains why I was not sure, but I was hoping that there will be no collisions. And it works. So, again, here is the collision discussions. Questions?
Is there any standard method or theory to know which constant, to know the constant correctly, so there is not going to be in the future collisions? I mean, what you explained about the constant Q, that if you choose it at random, we will have some problems, right? So, is there any step that we must follow to see, okay, this constant is going to work for my algorithm?
I think. So there are 2 constants, P and Q. In this solution, as I explained, we should choose Q randomly. Because we have a kind of a rule that random value will work good. But for B, it should be a prime number or vector or generator. So that basically, so the powers of P don't repeat in this. So if P is a prime number, then usually you have enough problems. I know, I always use 31. I mean, but it's up to you. Almost any prime number will work nicely. But for Q, you can just have in your program that is calculated randomly each time. You can also have just type in a random number. But it doesn't work. It doesn't work in composer, at least. It's theoretically possible that somebody during the challenge phase in composer will look at your solution and try to construct a case that fails your hash function. But in ACM, computation certainly work because all test cases are prepared before, so they have to have a test case against your hash. So. Okay, so that's problematic. Problem G. So nobody solved problem G, only original unconscious as well. It is a very difficult problem. Although the look of it is quite easy. So you ask to find maximum flow in the graph, but with some restrictions. And the graph is huge. So the number of vertices and edges is up to 50,000 or something like that. 10,000, but no, 100,000. Even worse. So, how do you solve this problem? And what was the problem about? The problem is you are given a network, which is a graph with capacities on each edge. And you need to find a flow in this network from the start to the finish. Or I think in this problem it was not start and finish, but it was several starts and several finishes, right?
Mm-hmm.
Yeah, so, but for each, so we have a network, which is direct. And that's important. Which has several points where you produce some liquid, and for each point you know how many liquid is produced. P. Was it? Yeah, it was like this P. So it's P1, it's P5. And then for some other points like consumption points, where liquid is consumed, so we have Q2, Q4. And you know that the sum of all production is equal to the sum of all consumption. And you need to organize the flow from all production points to all consumption points in such a way that, well, it is a flow. So for every vertex except production and consumption points, the amount of incoming and outgoing liquid is the same. And for a production point, the amount of outgoing liquid is more by the production amount. And the consumption point is less by the consumption amount. But, so this is kind of a standard flow problem. But, so how would the standard solution, what would the standard solution look like? We would add a new source, add edges with capacity equal to production amount to the all source, to all production points. Here I have edges with capacity equal to consumption amount into the sink, one big sink, and then run maximum flow from here to here. This, how would this, yeah, each edge has a capacity. So we have to use the maximum flow algorithm to find the flow. But all maximum flow algorithms don't run in not so quickly. More specifically, I think one can prove that no maximum flow algorithm can run faster than all of NM. I think. So there is a proof that no maximum flow algorithm can run faster than this. And this problem is too much. So no maximum flow algorithm will work. If you will get them fixed. But luckily, in this problem, you are not given an arbitrary graph. Your graph is very fast. So for every pipeline, the capacity of this pipeline is at least the total production, and which is equal to total consumption. And this is the first. And the second fact is that this graph is strongly connected. So from every vertex you can reach any other vertex. These two are stated in the problem statement. How does it help? First, the easy idea. Suppose that each capacity was at least twice total production. Then there exists a very simple solution. What is this solution? Choose any vertex of this graph. And let's name it root. Let's run a DFS from root along the edges. DFS will organize all edges into a tree, right? So as the so root, from which we have first edge, vertex and second. Here we have third and fourth. Here we have fifth. So we will get, and since the graph is strongly connected, every vertex is reachable from root. So we will get all vertices organized in such tree. let's find all consumption points in this tree. They are, in my example, 2 and 4. So these are consumption points. Let's make a flow from root to these points. How do we make it? For every point, so suppose this consumption is equal to, so here we need to consume 10, and here we need to consume 15. Then what do? We have a flow of 10 along this edge, flow of 15 along this edge, flow of 25 along this edge. So we go from top to bottom, and for each consumption point we give it as much as it wants. And when two are merged, then we give it the sum. So in the end, we have a flow from root to all those consumption points. Analogously, we can run a DFS on the reverse graph. So we get like this. This is root. Not on the reverse graph. So yeah, but yeah, the effect of the reverse graph. So we get a tree that from all vertices you can get to root. We find production points in this tree. So this produces 12 and this produces 13. And then we pass 12 here and 13 here. And since the total production is equal to total consumption, those will cancel at root. So 25 in cut and 25 at go. So then if you add up those two, you get a flow. Problem solved. You see? This looks very simple. But the catch is that it may happen that the same edge is both in this tree and in this tree. And because of this, the maximum amount of flow we can pass through each edge is 2 times the total production, not once. So in our problem, we're restricted to only once total production. So it is a problem. If our capacities were 2 times larger, this simple algorithm will work in linear time because DFS runs in linear time. So we need to somehow deal with somehow reduce the usage of such edges that are in both trees. And here, well, here comes the unsolvable part. So basically, this is a published article by Petr Jan and some other very famous computer scientists. And it's not, I mean, it's hard to figure out. So I can now read this, how they do this. I don't remember it myself. So the idea is not so difficult. What they do is they, when they go up along this tree and push the production up, they sometimes, when at some vertex, they see that this edge may become congested, so it may become overfull when we add up the rest. We leave some flow here and not pass it over, and then it is compensated during the second stage. That's the general plan. The details. Okay, let me try to. Or, I mean, that will probably not be so might make much sense because I don't really see any beauty in this construction. Is there a method list that I think we should follow or not? One minute. Is there a method list for this?
Yeah.
So I think the article is 4 pages. So I will just send this article to you if you are interested. You will read about this because I mean I can read it from now aloud, but it doesn't make much sense. So they restrict somehow the push, and then during the reverse push they use this information. But the details are, yeah, I will send them to you. So yeah, that's what this problem was about. But it was, I think, it was in the contest not for somebody to solve, but even the original contest. But rather to solve this funny fact that if the capacitors are big enough, then you can find the flow very quickly. It was kind of a problem, not for the sake of problem, but for the sake of advancing the common knowledge. So, yeah. But this might sound bad for guys who try to solve it, of course. Okay. So, done with this problem. I promise to send you the article. Okay, now problem H. This was the problem that very many chips tried to solve, but it required a lot of accuracy to get right. So, what was the problem about? You had a circular list of statements. And each statement was one of two kinds. Either there are X true statements, where X is some number, or next statement is true, false, is true or is false. One of those two kinds. And all statements were like this. And it was asked if there is a way to tell which statements are true and which statements are false, so that it is consistent. So if we assume that the given statements are true and they are false, and check each statement, then it will be correct. How do you solve this problem? First, consider the case where there are no such statements. All statements are of this kind. Next statement is true or next statement is false. That means that essentially, if you fix the value of one statement, so all statements are like this. If you fix the value of one statement, then next statement is true means that this value is equal to this value. And next statement is false means this value is not previous value. So if you go on the circle, you either copy the value or invert it. And thus there are really two choices. If the number of phrases that the next statement is false is even, then in the end you will end up with the same here. And this will be a consistent result. So if you set X to any value and go around the circle by changing X like this, you get a consistent set of values. And if the number of phrases next statement is false is odd, then after you go around the circle, you will get a contradiction. And the simplest one is when you have a circle of 1 that says next statement is false. Then this is a contradiction, so it is impossible. So when the number of the statements is odd, and there are no, all statements are of this kind, then the answer is impossible, otherwise it's possible and calculated to set one value to anything and then calculate losses. So in the first case. In the second case, when there is at least one statement of form, there are X true statements in total, in this case, you no longer have a circle. What I say is that if you take all statements of form, there are 3 true statements, for example, then your circle is cut because this statement does not depend on the next one. So for example, if you had this and this here, there are 5 true statements. And this set next is false. This set next is true. And this set next is true. Just for example. So essentially your circle is cut into several parts. Each part consists of statement of this form with several statements like this after it. Then for each part, we can calculate the following. How many statements in this part will be true if the first statement is true, and how many statements in this part will be false if the first statement is false. So for each part, if the first statement is false, we can determine the value of all other statements, and so for each part we get total true, total false, total true if true, total true if false. So if the first statement of this part is true or false, how many total true statements will be? And the other thing that we know for each part is this number. So how many does the first statement claim? So claim. So for each part we have these three numbers. Then how to solve our problem? Let's try all variants of which claim is true or neither claim is true. What if no claim is true? So no of those claims are true. Then the total number of true statements should be equal to the sum of this. Right? Because in each part the first statement is false, and then the total number is equal to the sum of these numbers. So how to check if it's possible? We should sum all those numbers, and then we see if this number matches at least one claim, then it is a contradiction. And then if the sum of those numbers does not match any claim, then it's possible that all claims are false, and that's the answer to the problem. So we set all claims to false and calculate all the rest by taking either negation or equivalence. You see? So this is the case when we suppose that all claims are false. Then if we suppose that some claim is true, more specifically we should suppose that all claims with the same value in them are true. So we check, for example, for 3. We take all claims of 3, then we should sum this value for them and this value for all other parts, and see if this sum is 3, is the value that we need to, that we are claiming is true. And if this is true, then we got an assignment of variables that satisfies the phrases. So again, we should take all claims with the same number, take the sum of this for those claims and this for other parts, and check if the sum is equal to this number that we claim. And if true, then we get an answer. How to do this quickly? Because the number of claims can be 100,000, so we can't just sum all those up. But if we know the sum of all these numbers, then in order to calculate what we need for a certain number, for a certain claim, we need to subtract this and add this for all claims that match. So we need to check then if the sum of, let's tell it, A1, A, E, B, E, C, E. So if the sum of C, E is equal to C, then first we need to check if C is not equal to any of AIs, and if yes, then we have found the solution. If C is not equal to some AI, we need to continue. We check each X, and for each X we need to calculate C minus sum over E such that AI equals X CE plus sum over I in which AI equals X BI. So in order to quickly calculate the sum, we take the sum of all and subtract what we don't need. Because of this will run in time equal to the number of A's which are equal to X. And the total number of such A's over all X is N. So we will do this exactly once for each E. And thus the running time of this will be linear. That's the final proof. Okay, questions about this problem? Okay. Then problem I. Problem I was probably the easiest problem because the code was literally 3 lines, but you had to get it right. There were, of those 3 lines, you could make thousands of possible mistakes. So, what was the problem about? The problem was you have a player that downloads that can download the video from the internet at d bytes per second. The video that you hope to watch video is at b bytes per second. The total length of video is t seconds. The player works in the following manner. At the beginning, it starts to download. It has a buffer of some size. Let's say it's S. So it has a buffer of S bytes, where S is an integer number. And how it works, it downloads S bytes of video, then starts playing video while downloading more. But since it was given, and the problem is that D is less than B, always, the rate of download is slower than the rate of playback. So at some time, he runs out of download data. At this point, it stops playing, and again fills the buffer until it is full, or until the video, or until it has downloaded all video, and then starts playing again. Okay, so all this means that there are some pauses when the buffer is empty. There's a pause before it becomes full and it starts playing again. And you request that each pause is at most p seconds. Okay, and the question is, what is the smallest possible s, such that each pause is at most p seconds? That was the problem. How to solve this problem? Let's consider one cycle of a player. One cycle is when it starts with an empty buffer, then fills the whole buffer, and then plays until the buffer is empty again. Let's consider this cycle. How long does this cycle take? In the beginning, we are downloading we downloading S bytes with the speed t. So it takes S divided by t seconds. This is what it takes us to download our buffer. Then after we have downloaded our buffer, after this we are showing the video at p bytes per second and downloading at t bytes per second. That means that our buffer is being emptied with the speed b minus t bytes per second. That's the speed that the buffer is being emptied. Okay? Does it make sense? So the time that it takes to empty this buffer is now S divided by t minus b. So this is the full cycle of our player. It takes so many seconds. Just a moment. I have not used. Yeah.